Thank you all for standing by and welcome to our webinar entitled Updating NOAA's Lake Erie Cyanobacteria Satellite Remote Sensing Time Series. This webinar series called Freshwater Science highlights Ohio Sea Grant and partnering scientists every month. Every quarter is a different focus, from human health and fish farming to harmful algal blooms and human decision making, bringing applied research to the public on issues that affect our Lake Erie communities. I am Jill Gentis-Banicki from Ohio Sea Grant and Stone Laboratory, and joining me today is Dr. Richard Stumpf from NOAA's National Centers for Coastal Ocean Science. Dr. Stumpf has decades of experience in coastal oceanography and harmful algal blooms. He has focused on the integration of satellite data, models, and field data to monitor and forecast algal blooms along our Great Lake and ocean coasts, with the goal of allowing people to use the water safely. He leads NOAA's efforts to translate forecasts of harmful algal blooms from research to operations. We're delighted to have him here today to talk about NOAA's time series. But before we do, just a few things about the webinar itself. During our presentation, all participants will be in a listen-only mode. Afterwards, around 12:20, Chris Winslow will conduct a question and answer session. If you'd like to ask a question during the presentation, please feel free to pull up that chat feature at the bottom of at any time during Dr. Stumpf's talk, and we'll collect and pose your questions out to Dr. Stumpf at the end of his presentation. As a reminder, this webinar has auto captioning and is being recorded to be posted onto our website for later viewing. Also, we will post a webinar survey in the chat feature toward the end of the half an hour. Please take a few minutes after the webinar to fill out that survey. It always helps us continue to bring you great webinars. So without any further delay, I'd like to introduce Dr. Stumpf, presenting Updating NOAA's Lake Erie Cyanobacteria Satellite Remote Sensing Time Series. Dr. Stumpf.
All right. Thank you so much, Jill, Chris, for having me. It's great to always be with Ohio Sea Grant. Many of you on the call probably know that we have had been using satellite data for a monitoring system for the cyanobacteria blooms in Lake Erie now. And we've been doing this for 15 years, and we've developed a 25-year time series on this. There have been some significant changes, improvements in how the satellites are calibrated, how they're processed, and how we work with it. And so this has caused us a need to reprocess our entire time series. So I'm going to talk through what that is and how the resulting data for this 25 years now looks compared to what we'd had before. I should note a lot of the work I have co-authors, as you can see here, and a lot of our work is supported not only by NOAA, but also by the Great Lakes Restoration Initiative that's run out of US EPA.
Rick, I don't think I'm seeing your screen. Jill, are you seeing his screen?
Oh.
No.
Yep.
Okay.
Looking better. There we go. Now I got your title slide with your partners. Thank you, Rick.
There's something special that happens at 12:01 here, and it messed things up. Okay. So just put a perspective here. Early 2000, or if we go back to the 60s and 70s, there were massive cyanobacteria blooms in Lake Erie, and at some point in the early 70s, Lake Erie was declared dead. The Clean Water Act was put into place. Point source pollution reduced, phosphates and detergents were eliminated, and the lake recovered wonderfully from that. But in the early 2000s, blooms reappeared. And the first, 2003, was, as you can see, was described as perhaps the most severe in recent history. Well, this went on, and a few years calmer, and then 2008, 9, 10, there were periods of extensive areas of scum, as you can see here. And this kind of peaked out in 2011 with potentially the worst bloom Lake Erie had seen. And it covered from Toledo to well past Cleveland over to Fairport area, well over 100 miles. And a lot of that bright green you see here is scum, which was truly extraordinary. So we've been working with satellite data, and of course, people are used to seeing pictures like that with bright green water. And when we work with it, just get a little sense of how we handle the data. You can see a true color image here on the left, and it's greenish water, but there's patches of various bright waters, some coming here, and different scales. It's very difficult to sort them out. Once we process the data, the bloom comes right out. And what I have here is a spectra, which is what we work with. Blue is here. If you can remember your Roy G. Biv, well, it goes red, orange, yellow, green, blue, violet. But the blue violet's here, green, and then red and near infrared. Sometimes we call the red edge, which is the edge of the red to the near infrared. The green on a bloom, it's green, but other things are greenish as well. And not all blooms are bright green. But when we go into this red edge, we get a lot of wiggles in the spectra. And so what we work with are these wiggles, and these are very distinctive to cyanobacteria. You can see there's a huge difference between a spectra from some other feature in that. This is what we use to work with. So we're reliably pulling out the cyanobacteria as compared to picking up, let's say, diatoms, which are the good algae, the base of the food chain, or sediment, that sort of thing. So when we're done, we have that scale from low to high. We relate this into the concentration of cyanobacteria in the water as well. So you can see the overall patterns, and also where it's not present at all. So with the satellite data, there are 3 missions you're going to hear about. 2 are MERIS, the MERIS sensor, medium resolution imagery and spectrometer. You don't need to memorize that, just call it MERIS. It was on a satellite called MVSat. And then OLCI, the Ocean Land Color Imager. And your fun trivia for today, it's pronounced OLCI, not OLCI or OLCI, because it's made in Italy. It was developed in Italy. And when they have a CI, they pronounce it CHI, OLCI. So your fun pronunciation for today for an acronym. They're best for cyanobacteria because they have those wavelengths in that, the key wavelengths in that red near infrared. Overall, they have a full range of data and works really well for that. MERIS was put in 2002 as a research satellite. It was expected to last for longer, but unfortunately, the satellite was lost in 2012. There's complete communication failure. And the OLCI was the replacement, which went up 4 years later. And of course, and OLCI is on 2 satellites now, I should add, Sentinel-3A and 3B. So there's an obvious observation gap. Well, we worked with the MODIS is on a NASA mission, and it's usable. It has some of those bands in that red edge, but it doesn't have all. It also, they saturate. The nature of it was designed for open ocean, not for lakes with intense blooms. And so you have to adapt around that a little to try to get it to work. So while it's not optimal, it certainly is usable to do this. So this is how we're approaching the data set, is putting these 3 together. Just to get a little better sense of them, the MERIS data that we work with is basically, it's about a 1 kilometer pixel. And it was about 1 to 3 per week. They had, they would actually record the data for a while to collect it, and then started using a Canadian site to download the data directly. So the amount varied per week depending on the ability to record it. MODIS is about 1 kilometer and a little wider swath, so there's about 4 per week. Again, it had fewer spectral bands. And then the OLCI, which is 300 meter data, so higher resolution. And I show an example here, same day, a MODIS and an OLCI. So you can see what a difference this makes. When you're at 300 meter, you're really at 10 times the resolution, or 9 times the resolution of a 1 kilometer. And so you can see how much sharper, including detail coming right into the shore. So Maumee Bay, for those who know that, this is the entrance to the Maumee River. Can't quite get in the Maumee River here, but we can get in very closely to the shore. So that information. And with 2 satellites with OLCI, it's we get an image almost every day with OLCI that's usable. The MODIS, you get trade-offs. You can actually get sun glint. I think most people experience that on a boat when the sun's reflecting off the water. So you lose some of the data there. So again, that's about 4 per week. So algae is long-term and it's going into the future. So we'll be using that for the next few decades. So we updated the time series, and why? Well, we have Maris. Our last reprocess was 2015, and there have been updates. There's a little more data became available, more accessible would be the better word, more accessible to us. Calibrations changed. Some other corrections were made, and so overall the Maris data was added and improved. We also drew on the overlap with MODIS to intercalibrate the Maris to Olchi to make sure that the product, our CI algorithm, the one I described earlier, would match between them. And also, we also need to try to adjust the frequency of Maris. If you're at 1 to 3 a week, you might miss a bloom. I'll touch on this a little later, but the simplest one is if you have clouds, if you have the bad luck during that week, that when the overpass occurs, it's cloudy, we can't see through clouds. And so you could miss it, whereas the next day when it's clear, you might not have an overpass. So that's a factor. MODIS Terra, our priority is to fill in that gap from 2012 to 2016, but with data from 2000 to the present, that also allows us to fill in the Maris data. We improved our MODIS detection over what we had before. And that was a better treatment, how we dealt with it when it's saturated, when the band's saturated, how we swapped out the bands and captured that. And a key part also is fill it where the Maris misses the blooms. Again, about 4 per week, and they're not on the same day as Maris. You pick up other days. Algae, Sentinel-3A went up in 2016. 3B went up in the end of 2018. And this past year, we finally, kind of the last major updates on calibrating the satellite. Once it's up in space, there's a whole recalibration done, changes in the atmospheric correction. And so a number of significant changes that we had implemented, which did change some of the numbers and data for algae. Pretty much all these changes, anything we have if going in the future will be quite small compared to what we've done here for these changes. This is all dealing with really substantive improvements in all that data. And again, algae, it's 300-meter data, which is better than we have before, and 6 or 7 per week. So the Maris and algae use the CI Cyanobacteria Index, which uses that red edge, the wiggles I talked about, and we quantify those. Been operational in Lake Erie for 15 years. We've been monitoring the blooms live that way. And also, I should add that the method has been implemented nationally in what we call the CYAN project, the Cyanobacteria Assessment Network. This is a joint interagency effort led by EPA and includes USGS, NASA as well, and 2,000 largest lakes in the country. And so what we learned in Lake Erie has extended across the country. That's one of the values of doing work in one area with a standard method. MODIS can use that approximation pretty well, but again, it saturates and under bright targets, and these blooms are often bright, so they target. Previously, we used the water turbidity to try to fix this. That worked okay, but we came up with a new solution with a neural net, a kind of machine learning, which we called CyanNet. And with that, in that approach, we match MODIS we forced it to match Maris and algae. So that way, when we had the gap fill, we knew it would align correctly. And so we put together the band combinations to ensure we could get the whole range. We actually developed this in Florida. So I mentioned Lake Erie allowed us to work elsewhere. So Lake Erie allowed us to develop the algae data set and Maris to apply in Florida. We took the MODIS, developed that, and then brought it back up to the Great Lakes. So this works across the country in both ways. So we developed it in Florida and we validated in Great Lakes. And that's a significant thing. Often machine learning becomes very tuned to the data set it was developed on. And in this case, we developed this in such a way that it can move from one place to another without having to redo it. And so just to show you how that overlap looks, we have the the Olchi against Maris, the Motus against Maris and Olchi. And these scatter plots, this line here is what we call the 1-to-1 line, which is when they both give the same answer. And you can see Terra and Olchi align extremely well over this. They're very close in Maris. Terra actually is a little higher, and mostly because it detects some blooms that Maris doesn't detect. That's the difference for it. But the alignment is great. You can see a time series where they follow pretty well. They should not match perfectly because they don't always collect data. What I would note is very tight relationship when we have the two Olchi on 2 satellites this one year with a big bloom, and we only had one Olchi. Olchi and Terra weren't quite, we're getting a little different answers just because of the frequencies. But the Motus aligns really nicely. So now we can build a data set off the 3. So the time series, there's one other step, and that's with the Microcystis, which is a dominant cyanobacteria. It's a buoyant species. Some of the others in the lake are also buoyant. And so we composite the data over 10 days. We don't work with the individual scenes. And we do that to what we estimate the aerial biomass, the total quantity of the cyanobacteria. Satellite sees the surface concentration. And if it's buoyant, that means on a calm day, all the bloom comes to the surface, and the surface concentration is capturing the bloom, the total bloom at that location. If it's a windy day, then you end up with it being mixed through the water column, so the surface concentration is lower because the bloom is dispersed through the water. So if we go over 10 days, we have a high likelihood of getting a cloud-free image and a low wind clear day to work with. So that way we're capturing how much was there during that time period. And so in addition, with these 10-day periods, then we can easily compare the results. And during that time, either Maris or the Motus or Olchi or Motus should capture the bloom as well. So that way we now have that information reduced. So we don't get this noise of one day there's a lot, the next day there isn't much, the next day there's a lot, the next day there isn't much as the wind change. So it gives us the total biomass. We call it CI units, but it's just the quantity of cyanobacteria. That's what the biomass is. One thing we will say when we put them together, we treat them separately, the Maris and Motus, but we assume Maris Olchi is better because of the uncertainties in CyanNet. So when we combine them, we assume to merge it that the CyanNet must be 30% higher just to account for that uncertainty. So that way we don't strongly bias the blooms upward. So when you look at this, this is the peak for each year from, I didn't include 2000 and 2001 because they were quite uninteresting. They're uninteresting. They were good. There were almost no blooms in 2000, 2001. 2002 had a very mild bloom. And you can go through these areas. What I'll just note, we've captured this out. So this is dominated by Maris. This is only Motus from 2012 to 16, but 15, and then the Olchi data set is in here. And you can see kind of the overlaps. 2011, severe bloom. 2015 was a bad bloom. And you can see how different they are. I would note particularly striking, obviously 2011 went way out to Cleveland, but also these areas would have been scum areas over on the Ontario coast. So anyone on the call from Canada, whereas in 2015, that was less. And you can see some of the others. Interesting, in 2017, there was actually scum from downtown Toledo all the way over to the Kingsville area in Ontario, clear across the lake. So it's a very dense bloom overall for that region. But you can see how much variation there are between either on the Ohio side or over on the Michigan side or also on the Ontario side. So when we look at it and time, how severe the blooms were, here we're showing our previous analysis, what we call pre-2024. So that's the data set we'd had till now. That's the gold brighter color. And then the biomass with our new project, our new process, 2024 and after, which is the dark green. First thing that stands out is, in general, they are higher now. The total biomass we're estimating is higher now than we had before. but keep in mind, everything would be a relative sense, but they're higher. And it's also tends to be higher earlier, which I'll just go through. So in the course of reprocessing this, the Maris data increased. The processing fixed some characteristics of Maris, added in more data. We also brought in the MODIS, so we're more likely to capture the bloom than we were before. Keep in mind, if we only had a couple of scenes in a week, the likelihood of missing the bloom because of clouds or high winds is very high. Now we had more data, both from Maris and from MODIS, and also our adjustments of the Maris changed that noticeably. And you can see how strong the 2011 bloom was, and it went on for what each bar is a 10-day period, and you can almost see 1, 2, 3, 4, 5, 6, 7, 8. That would be 80 days when it was actually in 2011 more severe than any bloom up till then. So 2012 to 2015 was only MODIS, and we had used a correction that wasn't optimal. It was the best we could do at the time to deal with saturation. So when we fixed that, and I should add in, Maris, we lost Maris in May 2012, and the bloom started in July, and we didn't have anything for MODIS at the time. So in 2 months, we went from knowing nothing to having MODIS functional. So we had to improvise here a fair bit. And we did pretty well, but we found in the course of the next couple of years that we were off on how to deal with the high intensity blooms. So each year it changed. So when you notice how 2012 and 2013 are much different now than 2014 and 15, that reflects the fact that we didn't use the same process at the time because we had to change it each year as we got better at it. And so now it's all a consistent process for those times. The last ones here is Ulchi went up in 2016, 3 on 3A and on 3B in 2019. And Ulchi and MODIS together picked up a bit more of the 2017 bloom. And then now it's pretty much all Ulchi. And this reflects, these adjustments are this recalibration atmosphere correction changes. So there was no previous one for 2024, in case you're wondering. So this is all the new data set for 2024. So how does this translate into the severity index we have? Well, our severity index was set so to the peak previously 2011, where 2011 was assigned to 10. 2011 is still the peak, it's the peak bloom. And so we set that to 10. So the severity index for each year is the peak 30 days of the bloom. And the uptimes, so the current time series definitely better captures 2003 to 11, and you see the relative intensity has increased. The previous one that's these dark, the circles. The recent years looked about similar to 8, 9, 10. And what we find once we reprocess it is that 8, 9, and 10 were worse than this year. So these didn't get milder, I should emphasize it. They changed relative to 2011. Everything up to 2011 is worse than we thought it was. So they are much worse blooms than they are now. So these blooms are in fact more severe blooms than what we have seen in these recent years. And so we're capturing a more accurate input. 2011 was the most severe bloom, followed by 2015, 13, 17, and 19 as well. And 2003 is a bit more severe than we had originally thought. Just to show it a little different way, and right now we have at least a descriptor of how the blooms are. And if we're at about a 3, if we're up to about a 3, we'd call this a mild bloom. And of course, a couple of these years are right at that 3 level. 3 to 5 is a moderate bloom. 5 to 7 is severe, and then very severe is greater than 7. And those, and I should add in, you'd have to be a little careful on how people view these, because you could be, say, Maumee Bay often has a problem, unfortunately, where the state park is. And you could have a scum in that area for weeks on end, and that's a really severe bloom for that area. Whereas, the overall bloom in the lake may not be that severe. We could also have a very severe bloom out away from shore towards the center of the Western Basin. And that would appear kind of mild near the shore. So it does change quite a bit. So a caution here on, experience of anyone boating or going, to the water in any particular area, your interpretation of it will be different. This is something we're thinking at and looking at in the phenology to try to capture some of the frequency and the other information to get a better sense of that for areas. Something else I'll add on this, which probably I'll just might catch attention, is it sort of looks like it's better. Obviously it got worse, and then these blooms are more severe than these. Well, it may be tempting to draw the conclusion that we're seeing actual changes resulting from the management, and I would say that it's premature at this time. The reason for this change has to do with the amount of water coming out of the rivers, particularly the Maumee River. And so from 2008 to 2015, the river discharge was all above the average except for 2012. And in these last several years, it's been below the average. And lower flow means lower phosphorus loads. The concentration of phosphorus, which really tells us how we're doing, has been about the same over this time. But by having simply less water, that means we've ended up with a smaller bloom. And so if we go back to higher than average flows, then until we start getting the phosphorus going into the river down, we will very likely go back to those sorts of blooms. So just a very cautionary that these changes, we have to keep in mind the influence of weather and river flow on these concentrations. We do a seasonal forecast, and one of them is with a model with the TPB is the total bioavailable phosphorus. That's the amount of phosphorus. That's the phosphorus in the water that the cyanobacteria can use. Some phosphorus is actually bound to sediment and it's not available. So we look at this, and so we've updated our relationship. If it's pretty much, you can say if it's going to be above about 500 metric tons of load between March and July, there's going to be a severe bloom. That's 2017, 11, and 15. And then you capture down, once you're down on this level around less than 300 micrograms, you're down, or metric tons, you're down on the lower end. And so we use here's the comparison between these. We focused on the recent years for the validation 2013 to 17. In general, it works well overall for the bloom. And that gets to where we are in the forecast. We have started our early season forecast for the lake. The loads that drive the bloom are March to July. And so we now have 2 months worth of actual measurements. Phosphorus concentrations come from Heidelberg University, and they collect samples at a U.S. Geological Survey gauging station on the Maumee River as well as other places. So there's a whole combined effort. We use a forecast model from our Ohio River Forecast Center out in Wilmington, Ohio, as far as what the river discharge will be for the next 2 months. And so once we're in early May, we have 2 months of data, and we're looking for another couple of months. So right now we're looking at based on the forecasted loads, which you can see on this graph. We have uncertainty here as far as the range, but we're looking at probably between a 2 and a 4.5. So that could be between potentially a mild bloom to a moderate bloom, but probably something that would look similar to the last few years as the forecast. So our updated time series across the missions, our previous work on this was 2015. And that was all prior to the actual launch of the Olchi satellite in Olchi sensor in 2016. This much better captures the blooms in that what we call the modus maris period, which is from 2000 to 2016. So we have those down now. Far more complete. That's how we capture it. We have a much more complete record. Modus is now more consistent, more accurate than we had before. And I should say previously, the 2008 to 10, those blooms had looked similar in intensity to recent blooms. And what we have determined, in fact, is that those blooms were more severe than the blooms we've seen in the last few years. So 2008, 9, 10 were definitely more severe blooms than 20, 22, 23, 24. If you need to reach us, there's a QR code and a contact. So thank you very much.
So Rick, we're right at time, actually a minute over. There are some questions coming in. The one I do want to highlight here is what Sandra mentioned. I love your graphic of showing, the new calibration and also the flow. So it's shown as Q on the vertical axis for those that aren't familiar with flow. So again, it seems like when you have wet years, you have big blooms, and dry years, you have lower blooms. But I want to point to what Sandra has, and she's talking about a new model, the WRTDS, which actually kind of normalizes what the bloom would look like in the nutrients without trying to remove that flow. So it looks at time and discharge and season, and we are seeing that the concentrations in that model shows a decline in phosphorus. Not, if you talk to the academics, not statistically so, but we are definitely seeing a downward trend despite the tight relationship between your severity index and also the flow, or what's called Q in this graph. So thank you for pulling it back up again. We have a lot of questions coming in here. A lot are talking about budget cuts and how it might impact us. Know that I've talked with Rick. Rick and his team are going to be able to do this forecast throughout the summer, and know that a lot of state and federal agencies and academics are still out there working really hard to collect the data to inform this forecast, but also progress on the edge of field and in communities. And so that's great. If you have to drop off, we get it. We're recording this. We may run a little long. Cal, if you can unmute, I see you have 2 questions here, so it would be good if you could, rather than me reading that, can you ask Rick the question that you've posted there? If you can't unmute, I can read them. Let's try it my way.
I can see if I can unmute them.
If not, I can read it. So the EPA, Great Lakes folks, so the HAB goal was previously expressed in no worse than a 2012 in 9 out of 10 years. I believe the report actually said 2012 and 2004. At the time, both would have been considered mild in terms of messaging. It seems we should now avoid saying our goal is to be no worse than 2012, considering 2012 was much worse than we thought. And it is now considered a moderate bloom. Excuse me. However, in terms of the end goal, the amount of biomass for what are considered a mild has not changed, correct?
I would say yes, that's correct.
Good.
That biomass has not changed. 2012, I should say, was a very small but phenomenally intense bloom. And so because it was so intense, it was our original analysis missed that intensity. So from area size, it was unusually, it's like out of proportion how intense it was. You could picture a small patch of scum, but I would say the biomass goal doesn't change.
Good. And so that's what he's asking. In terms of the end goal, the amount of biomass, what's considered mild has not changed. You're saying, no, it hasn't. And so then he comes on to say, should we coin no worse than 2004, or avoid saying a year in the event that the assessment changes again in the future? So what would your recommendation be? Just say 2004, or just
2004 has crossed my mind, yes, as an appropriate one. And okay, we're not going to see and we don't expect to reprocess it anytime soon, and we're not going to see any changes like we've had with this one, because there's so much that went on that is now systemized. Besides the fact that Olchi, it's on 2 satellites, then European Space Agency they're ready to launch the next 2 or the next one, and they've got 4 more lined up. So we're looking at probably 20 to 30 years of exactly the same satellite sensor, which will make this so much easier.
Good. Rick, I want to get to the last one because we all know Tom Henry does some great, articles about the bloom and progress. He's saying, so just to be clear, are we now saying 2015 was not the worst year and is now second to 2011? That's the first question. And the following on that, and I can hit on this, is how will that change management strategies? So, Rick, about the 2011 versus 2015, is 2011 now officially based on this?
2011 now is officially the worst bloom. Yes.
Thank you.
It was the biggest, most extensive bloom.
Good. And Tom, I encourage you to reach out to Rick. He's got his email on that last slide. And then as far as management strategies, no, right? We know what the target is. And as we've said here, right, we know what the biomass target is for us. That's not changed. Cal asked the question, Rick answered. And so we just know we need to keep cutting dissolved reactive phosphorus, more specifically the bioavailable phosphorus. We know a lot of those strategies and what we need to do. This is a continued investment in those strategies and also studying some of the things we're recommending, right? So when we say subsurface placement, are we doing it the right way? Well, when we're using our manure, have we found the right way to apply it? When we work with communities, suburban and urban locations, are we doing the right thing? So, Tom, I would answer, no, we know what the strategy is. This is just a calibration that has moved 15 below 11. Rick, any comments or additions to that, or are we good?
Probably one, as I happen to have this up, you notice that from 2000 to 2007, the discharges are somewhat similar to recent years, but the phosphorus going into the lake, the bioavailable, was about half of what it is now, approximately, little in that neighborhood. And so, so those years had smaller blooms because there was less phosphorus going in, even though the same amount of water was going in. And so if we can get all those things you talked about, Chris, if we get those management strategies in effect, we can get that phosphorus concentration down, which will bring those loads back to what we were looking at in the early 2000s.
Tom is asking about how will this confuse the public, given that many farmers don't even believe ag is the biggest issue. So again, Tom, you've been in this game for as long as Rick and I have. This is a lot of not only deploying practices, but working with farmers to see some that may not be doing the practices, or those that are doing the practices and be tweaked. So as far as greater confusion, I'd be happy offline, Rick and me, to sit with you, Tom, and help you get some talking points here. I really don't think this is a change in what we've been doing as far as management strategies and trying to address phosphorus. It's just elevated the confidence in NOAA and more specifically NCCOS in what that index is for every year. And so that's where we're at. Peter, thanks for your comment there. Thanks for that. This will be, as Jill has said, it'll be recorded. It will live on the website. So if you haven't copied it and made this website one of your favorites, there are many, many forecasts like this in there, or not forecasts, webinars in there. We encourage you to go to it. Rick and I will go through the questions that we weren't able to answer here in the chat function and those that were submitted ahead of time. And perhaps we can burden Rick with putting a sentence or two to answer those questions that came in. Rick, any parting words before I turn it to Jill for parting words?
I can say is follow our forecasts, and if there's whatever bloom there is not covering the whole lake. It's not covering the whole Western Basin. There will be plenty of great places to go swimming and boating on the lake.
Cal, I encourage you. So and we can talk offline too, Cal. If you look, what Rick was referencing is if you look at the flow that came down in 2000 to 2005 was equivalent to the flow we've seen like in the last 4 years, but the blooms were smaller. So clearly we have a phosphorus increase in that water from that early 2000s to currently, which again is our goal to recognize where those inputs are coming from and how do we address them. Jill, anything for you?
No, just a big thank you to Dr. Stumpf for his willingness to talk to us today. And I just wanted to also remind everyone that we have a survey URL for this webinar in the chat feature. So if you can take a few minutes to fill that out. And then lastly, that this webinar series is sponsored by Ohio Sea Grant and will continue next month with Lake Erie's HABs forecast, June 26th. I put that registration in the chat feature as well. Thank you again, Dr. Stumpf, and all the participants on this webinar. We hope this was beneficial, and we hope that you'll join us in an upcoming webinar. Thanks again, Dr. Stumpf. This was great.
Yeah, thanks, Dr. Stumpf. I just put my
Thank you so
email
much.
in the chat, and David, thanks for the kind comment. And again, let's work about this messaging. This is not a manipulation of the data. This is trying to fill in gaps of data that was not as detailed as we needed it and wanted it to be. And Rick and his team have found a way to recalibrate so that we're doing our best. So it's not a manipulation of data. It's a reanalyzing and a calibrating of data. Thanks, everybody. Tom Henry, if you want to reach out to Rick and I know you have your emails. We're happy to have conversations offline. Everybody have a great day. Jill, thank you very much. Rick, thank you very much.
Okay, I'll catch up
Thank
with
you.
Take care.